In section 6.5, we're going to look at how we use mole-to-mole and mole-to-mass calculations to solve problems in chemistry. And in particular, we're going to learn how to solve a very common problem called a grams of A to grams of B calculation. So we'll show you a few examples of this. This is probably the most common type of calculation that people will do involving moles and mass. So the key to performing this type of calculation is knowing the mole ratio that relates the amount of a reactant to the amount of product that you're interested in. You're going to get this from your balanced chemical equation. In addition, you will also need the molar masses of the things that you are trying to relate the amounts of. And if you have this information, then you can calculate the mass of product from a given mass of reactant, or vice versa, the amount of reactant needed to calculate a given mass of product. So a good example of this is given in this next problem. So it says, if 28 grams of methane is reacted with O2, how many grams of water is produced? So we recognize this immediately as a grams of A to grams of B problem. A is the methane because we have the grams of methane, and B is the water because we would like to know the grams of water. So the first thing that we're going to need is a balanced chemical equation so we can find out our mole ratios. So let's go ahead and write the balanced chemical equation for the combustion of methane to produce water, and it also produces CO2. So you can see here we're starting with 28 grams of methane, and we would like to know how many grams of water can we produce. And importantly, we can see that for every 1 mole of methane reacted, we produce 2 moles of water. So to calculate the mass of water produced, I'm starting with my grams of methane. And the first thing I'm going to do is I'm going to turn that into moles of methane by multiplying by 1 over the molar mass. And hopefully you can see that that will cancel out the grams of methane. So my first conversion here leaves me with moles of methane. Now I can use my mole ratio. And according to my balanced equation, I produce 2 moles of water for every 1 mole of methane reacted. So multiplying by the appropriate mole ratio that cancels moles of methane and leaves us with moles of water gets us a little bit closer. Now, in order to turn moles of water into grams of water, which is what I want, I need to multiply by the molar mass of my water. So I know that there are 18.02 grams of water in every 1 mole of water. And so by multiplying by the molar mass of water, you can see that moles of water cancels out, and the only unit left is grams of water. And so there's my answer. So I would put all of that into the calculator, and for 28 grams of methane being reacted, I could produce 62.9 grams of water. So it's a little tricky to keep track of everything that's happening there, but you'll realize once you've done a few of these that it's the same procedure again and again and again. What you're going to be doing whenever you're doing a grams of A to grams of B conversion is you're going to be multiplying by 3 conversion factors. First of all, you're going to take your grams of A and multiply it by 1 over its molar mass. That'll give you the moles of A. Once you have the moles of A, you're then going to multiply by the appropriate mole ratio. This will have the coefficient of B on the top line, the thing you're trying to find the grams of, and the coefficient of A on the bottom line, the thing that you knew the coefficient of. And this will give you moles of B. Once we have moles of B, we'll multiply by the molar mass of B, and that'll directly give us the grams of B. So our pathway is grams of A to moles of A to moles of B to grams of B, and we're always going to be multiplying by the same 3 conversion factors. So it's not too tricky once you get the hang of it. we're going to be using the molar masses of A and B and the mole ratio that relates the amounts of A to the amounts of B to solve all of these problems. Once you realize that, they become somewhat simple. So here's another example, but in this case, we're going from the amount of product to the amount of reactant that would be needed to produce that product. So it says, to produce 15.2 grams of Fe2O3, how many grams of O2 are required? And again, we immediately recognize this as being a grams of A to a grams of B problem. In this case, the Fe2O3 will be our A, the thing we know the grams of, and O2 will be our B, the thing that we would like to know the grams of. So before we can get going, we need to balance the chemical equation so that we can get the correct molar mass. The correct molar mass? No, the correct mole ratio. Once we have the balanced chemical equation, we can go ahead and set up our grams of A to grams of B calculation. So we start with our grams of A, and then we multiply by 1 over the molar mass of A, and that will eliminate the grams of A, leaving us with moles of A. Then we're going to multiply by our mole ratio. We're going to multiply by the mole ratio that has the coefficient of our unknown on the top line and the coefficient of what we do know the grams of on the bottom line. And hopefully you can see that that will leave us with the moles of our B. And then finally, to turn the moles of our B into grams of our B, we have to multiply by the molar mass of our B. And that will cancel moles of our B, leaving us with the grams of O2 or the grams of our B, the thing that we are interested in. We multiply all of that together in the calculator and we get our answer. So just reiterating, it goes grams of A times 1 over the molar mass of A times the number of B's over the number of A's times by the molar mass of B will give you the grams of thing B. And that's how we do it. So this is an example from the book. It says the oxidation of propanol to form propanoic acid has the following chemical equation. And then there's a pretty complex chemical equation there. It asks how many grams of propionic acid are produced by the reaction of 135.8 grams of K2CO2O7. So I'm going to need a few things to make this work. I'm going to need the molar mass of K2CO2O7, which I added up earlier, and that works out to be 294.18 grams per mole. I'm also going to need the molar mass of my propionic acid, and that works out to be 74.08 grams per mole. And then I'll be needing the mole ratio that relates the amounts of those two things, which I can get from my balanced chemical equation. So let's put all of this together. I get 135.8 grams of K2Cr2O7, and the first thing I'm going to do is multiply by 1 over the molar mass of my A, which is 294.18 grams per 1 mole of the K2Cr2O7. Now I have to multiply by my mole ratio, and I get 1 mole of the propionic acid for every 2 mole of K2Cr2O7. And then finally, I'm going to multiply by the molar mass of my B, my propionic acid, and there are 74.08 grams of propionic acid in every 1 mole of propionic acid. And if I check my units, the only unit that should remain is grams of propionic acid, and I can go ahead and put that into my calculator. So 135.8 times 1 over 294.18 times 1 over 2 times 74.08. And there we are. We're going to give this to 4 significant figures. So it ends up being 17.10 grams of propionic acid that can be made from that amount of potassium dichromate. Okay, so that's a classic grams of A to grams of B problem. You'll need the molar masses of both your A and your B, which you'll have to add up, and then you'll need your mole ratio, which you're going to get from your balanced chemical equation. You then just need to put them together in the correct form so that you get the units for what you want. Okay, so that concludes what we'll be working on in Chapter 6, and we now know how to do grams of A to grams of B calculations, which is a major achievement.